Hello and welcome to this session on the asymptotic solutions of differential equations. So, in the previous lecture we have considered the asymptotic solutions for algebraic equations, where we saw the distinction between regular perturbation and singular perturbation. In this particular lecture we will try to cover regular perturbation as applied to ordinary differential equations. The method of applying it to partial differential equations is relatively similar, and hence it will be covered in the due course of the course. So, let us consider considering the differential equation y double prime plus 2 epsilon y prime minus y equal to 0 subjected to y 0 equal to 0 and y 1 equal to 1, where epsilon is a small parameter. Let us consider the solution when epsilon is identically equal to 0. So, the solution for this can be done by assuming y equal to e raised to mx, therefore, m square minus 1 equal to 0, implying m equal to plus minus 1. So, the solution y is equal to c1 e raised to x plus c2 e raised to minus x. So, 0 is equal to c1 plus c2 when we use boundary condition 1, and 1 equal to c1 e plus c2 e raised to minus 1. And so, the solution for this may be found out by multiplying the above equation by e raised to minus 1. So, we have 0 equal to c1 e raised to minus 1 plus c2 e raised to minus 1, and then subtracting this equation from this equation. So, we have 1 equal to c1 e minus e raised to minus 1, and the c1 equal to 1 by e minus e raised to minus 1, and the c2 by using this equation is equal to minus 1 by e minus e raised to minus 1. Hence, the solution for epsilon equal to 0 is equal to 1 by e minus e raised to minus 1 times e raised to x plus c2, which is minus 1 by e minus e raised to minus 1 e raised to minus x, is nothing but e raised to x minus e raised to minus x by e minus e raised to minus 1, which is equal to sin h of x by sin h of 1. Let us see how the plot looks like. So, let us create a script. Let us define x as a Lin space 0 to 1. Let us take 20 points. So, let us write y is 0, which is the base solution, as sin h of x by sin h of 1. And in figure 1, let us plot this. Let us save it in our folder. And there we have it. So, now let us try to account for how the solution deviates because of a non-zero value of epsilon. So, let us try to solve this particular equation without letting epsilon become 0. So, we have y equal to e raised to mx as the prototype form of the equation of the solution, and thus we have m square plus 2 epsilon m minus 1 equal to 0, which implies m equal to minus 2 epsilon plus minus under root 4 epsilon square plus 4 by 2, which is also equal to minus epsilon plus minus under root epsilon square plus 1. And so, if we call the solutions as m1 and m2, m1 equal to minus epsilon plus under root epsilon square plus 1 and m2 equal to minus epsilon minus under root epsilon square plus 1. So then the solution y equal to e raised to m1x plus e raised to m2x, and using the same boundary conditions, y0 equal to 0, y1 equal to 1, we obtain 0 equal to e raised to there should be c1 and c2 over here. So this is equal to c1 plus c2, and similarly 1 is equal to c1 e raised to m1 plus c2 e raised to m2, and then once again we can multiply the first equation by e raised to m2. So we have 0 equal to c1 e raised to m2 plus c2 e raised to m2. Subtracting this from this, we obtain c1 e raised to m1 minus e raised to m2 is equal to 1, which implies c1 equal to 1 by e raised to m1 minus e raised to m2, and thus by making use of this equation we have c2 is equal to minus 1 by e raised to m1 minus e raised to m2. So the solution is y equal to c1, rather e raised to m1x by e raised to m1 minus e raised to m2 minus 1 by e raised to m1 minus e raised to m2 e raised to m2x. Let's try to plot this equation for a particular value of epsilon. So let's say epsilon is equal to 0.1. So y exact is equal to e raised to m1x by let's times c1 plus e raised to m2x times c2, where c1 is equal to 1 by e raised to m1 minus e raised to m2, and similarly c2 is equal to minus of c1. Okay. So after defining this, we say hold on, because we want to plot the figure on the same plot, x comma y ex, and let's denote it by a dashed line. Okay, so we have forgot to define what m1 and m2 are. So as defined over here, m1 is defined in terms of epsilon. So m1 is equal to minus epsilon plus square root of epsilon square plus 1, and epsilon 2 is simply this, m2 is simply this. Okay. So because of the presence of a non-zero epsilon, the solution is shifted over here. So now clearly the solution for small epsilon is not so far away from the exact solution. So the solution for epsilon equal to 0 lies very close to the solution for small epsilon. This implies that the solution is some sort of correction to the solution where epsilon is equal to 0. This indicates that the procedure to be followed here is regular perturbation. Moreover, as we had observed in the previous class, because epsilon is small and by setting epsilon equal to 0, we are not compromising the order of the equation, and thus we can easily proceed without much hassle. Okay. So let us see how we can do this problem by means of regular perturbation. So just to reiterate, the question is y double prime plus 2 epsilon y prime minus y is equal to 0 subjected to y0 equal to 0 and y1 equal to 1. So, let us write the solution in the form y equal to y0 plus epsilon y1 plus order epsilon square. If you are interested only in finding the first two terms, the leading order term and the first order term. So, let us write down what y double dash will be. This will be equal to y0 double dash plus epsilon y1 double dash plus order epsilon square. Similarly, y dash will be y0 plus epsilon y1 dash and so on. And thus, if we substitute A, B and C in the GNU equation, we obtain y0 double dash minus y0 plus epsilon y1 double dash plus 2 y0 dash minus y1 plus order epsilon square equal to 0. Similarly, if we substitute this kind of expansion in the boundary conditions, we have y0 plus epsilon y1 plus epsilon square order epsilon square is equal to 0 at x equal to 0, implying y0 equal to 0, y1 equal to 0 and so on, all at x equal to 0. And similarly, using this condition, it is easy to show that y0 equal to 1, y1 equal to 0 and so on at x equal to 1. Okay. And thus, at order epsilon dash to 0, we have y0 double dash minus y0 is equal to 0, which is subjected to y0 equal to 0, rather let us write it down in this way, and y0 x equal to 1 equal to 1. Solution for this is exactly what we had obtained earlier. The solution is simply y0 equal to sin h x by sin h1, which is the leading order solution. This is nothing but the leading order solution, and thus let us go to the first order solution. So, at order epsilon, we have y1 double prime minus y1 is equal to minus 2 y0 prime, and y0 prime is equal to cos h x by sin h1. This is equal to minus 2 cos h x by sin h1. So, let us write down the solution y1 equal to y1 homogeneous plus y1 particular, where y1 homogeneous is simply a sin h x plus b cos h x, because y1 homogeneous has to be the solution of y1 homogeneous double prime minus y1 homogeneous equal to 0. And because of the because of the fact that m equal to 1 in this case, and this form will lead to a denominator equal to 0 if we apply the method of Heaviside, and then y1 particular has to be of the form cx into sin h of x. Okay. So, all this is very trivial and is possibly covered in the first year of undergraduate courses. And proceeding with this, let us see what we obtain using the boundary condition that y1 at x equal to 0 is 0 and y1 at x equal to 1 is also 0. So, we have b equal to 0 directly, and then we also have A sin h1 plus C sin h1 is equal to 0, implying C equal to minus A, and thus the solution y is equal to sin h x minus x sin h x times A is also equal to A sin h x times 1 minus x. So, y 1 double prime, let us see what that will be. So, before that let us just write down what y 1 prime will be. It will be equal to cos h x minus x cos h x minus sin h x times A. Similarly, y 1 double prime will be sin h x minus cos h x minus x sin h x minus cos h x times A. But sin h x times 1 minus x, these two terms simply yield y 1, and then we have minus 2 A cos h x. Thus, y 1 double prime minus y 1 is equal to minus 2 A cos h x, which is also equal to minus 2 cos h x by sin h 1 according to this particular equation. So, this is equal to this, which clearly implies that A has to be equal to 1 by sin h 1, and thus the solution y 1 is equal to 1 by sin h 1 times sin h x times 1 minus x. Hence, the solution y is equal to y naught, which is equal to sin h x by sin h 1 plus epsilon times y 1, which is equal to sin h x by sin h 1 times 1 minus x. So, let us try to plot this asymptotic solution. So, there we are. The solution matches very well with the analytical solution. The black line, okay, let us put a legend, let us not have to strain for it. So, the first plot that we did was the leading order solution, and then we plotted the exact solution, and then we plotted the asymptotic solution. All right. So, clearly the exact solution and the asymptotic solution very much overlap. They have a very slight difference amongst them, which does indicate that the regular perturbation solution works. In fact, we will see that the larger the epsilon becomes, the worse the solution starts to behave. Let us see what happens for epsilon 0.5. Not so bad if you ask me. Let's see what happens when epsilon exceeds becomes very close to 1. Now we see that the solution is starting to deviate larger. So the correction to the leading order solution is quite large, but still it's going nearer to the exact solution. And we expect that as epsilon becomes larger than 1, the solution should not match. Okay. So the fact that it match, I mean it's still close to each other, indicates that the correction to these first two terms will not be very large. In general, we don't know exactly what the next term in this series will be, but as a leap of faith, we usually try to go with maybe 2 or 3 terms, depending on the problem, of course. And a good fluid dynamicist is always driven by physical intuition, because in such kinds of problems where we have regular perturbation, usually there will be some physical parameter that will be small. Maybe it's Reynolds number in the case of Stokes flow, in the case of diffusion maybe it's the Peclet number, and so on. So good physicists and scientists are not blindly following these methods, but when the problem is made dimensionless, various parameters come out of the problem, and these parameters can be usually large or small depending on the physical problem, of course. And then it indicates that yes, the solution must behave at the leading order in some manner, and then based on that solution we can then find out what the behavior will be as that parameter starts becoming large. Okay. For example, if Reynolds number is exactly equal to 0, it behaves like a Stokes flow, but even if there is some amount of inertia present, it leads to some kind of correction to the flow, some kind of inertial effects start coming into picture. And so with this we wrap up regular perturbation, and hopefully these small MATLAB sessions or Octave sessions are helpful for someone who wants to get involved in, not just finding exact solutions and plotting them, but trying to see what kind of corrections one obtains when one does a kind of corrections to the leading order solution. So here in the case it was a black line and it got corrected to a red line. So in the next lecture we will consider an example of singular perturbation, and then we will see how problems involving large Reynolds number can be reduced to such a kind of problem. So I will see you next time. Thank you. এটা শেষ, এরপর আরেকটা হবে।